This section in lesson 2.2 focuses in on the number of possible zeros a function has and the possible number of turning points a function can have. Zeros are the places where it crosses the x-axis. Turning points are a nice way of saying where does it have maximum and minimum points. Where does our curve go from increasing to decreasing, or vice versa. So turning points. Here's a turning point because our graph goes from a decreasing graph to an increasing graph. Here's a turning point because it goes from an increasing to a decreasing. Anywhere we have a relative max or min or an absolute max or min is called a turning point. This graph has 0 turning points because it never goes from an increase to a decrease. It's always increasing. So we can have 0, or we can have 2 turning points, as you see there. And there's a quartic function. Quartic is a nice way of saying a 4th-degree polynomial. But a 4th-degree polynomial, as we looked at those monomials earlier, it could have 1 turning point, or it could have 1, 2, 3. I'm going to look at this point a little bit more in depth with you about how many turning points a quartic and a cubic can have, and for that matter, any degree polynomial. And that's really what we want to nail down is, I don't care what degree of polynomial they give you, you'll be able to look at that leading term test, and you can say from the exponent how many turning points it has and how many possible zeros there are, which is fairly important when you start solving polynomial equations. So what we're going to do is I'm going to go through and I'm going to show you some different variations of the graph on a different program here to show you how many zeros there can be and how many turning points there can be. So right now I'm just graphing the basic function y equals x cubed. All this other stuff that you see back here, those are control modules for the parameters and how I can change the shape of the graph. And you don't have to be overly concerned about that. I'm just going to show you some very quickly, hopefully, the different shapes of this graph. So here is our parent function. It's strictly increasing. There's 0 turning points, and there's nothing I can do to this parent graph without changing anything real major, without sliding up and down. But I want you to focus on how many times it crosses the x-axis, and no matter how I move this, it has to cross the x-axis at least once. With any odd function, and this happens to be an odd function, it's guaranteed to cross the x-axis once because the opposite end behavior. You can see up here it goes to positive infinity, down here it goes to negative infinity. Every odd function is guaranteed at least one x-intercept, or 0. But this is the most boring of the graphs, so if we want to liven this graph up a little bit, then I can change the shape of it and get it to look more like our dynamic S. If I do this and I ask you the question, same questions, how many zeros does it have? We should be able to figure out that there's 1 0 here at 0, 0. I'm not pointing to it exactly, but just trying to highlight there's a 0 here and there's a 0 there. So this has 2 zeros. How many turning points does it have? Well, it went from having 0 turning points to 2 turning points, and that's the point that we want to articulate. No matter what I do with this parameter, it's just going to make it a little bit more dynamic as far as an S shape, but it only is an S shape. So if we come back to this, 0 turning points, 1 x-intercept. If we do this, maybe we end up with 3 x-intercepts, but 2 turning points. This is the one I want to show you as I move it up and down. How many zeros are there? At the least, the smallest number is 1. It could have 2 zeros, or it could have as many as 3. Now 3 is the maximum. You'll never get higher than 3. So that's what we're focused on, and that's what I want you to be thinking of as we listen to this. The next thing is, how about turning points? The maximum number of turning points you could have is 2. As you can see in this graph, there's 2 turning points here, 1 here and 1 here. And even though I try to make it a little bit more dynamic and I move it around by using these parameters, I either go from having 2 of them to, well, still 2. I can move this around a little bit and I can get it back to 0 turning points. So here's what I want to summarize, and I'll show you one other thing. I've always had A as positive, but what does A be a negative do? Flips the graph across the x-axis and it goes from a high to low graph. So all the negative is for this A is going to change it from a high to low versus a low to high. So quick summary on this, and we're going to go to the cortex. So on a 3rd degree polynomial, what is the number of zeros that you can have? The maximum number is the degree of the polynomial. Since it's a 3rd degree polynomial, it can have a maximum of 3 zeros. It could have 2, it could have 1, but it will never have 0 because of the end behavior. How many turning points will it have? I'll abbreviate that TP, the number of turning points it can have. The greatest number of turning points it can have is 2, but it could also have 0. And again, this is the graph that has 2. If you want to have one that has 0, I can drag it, and we've shown you that before, so we'll move on. So next thing I want to do is show you some graphs of quartic. The quartic graphs, I'll switch to a different equation here and graph it. I want to bring back to the most basic and boring quartic graph, which just is the monomial, where it says y equals x to the 4th. Every even polynomial has to have a U shape. Every odd polynomial had to have that S shape that we saw with our cubic. So here's our 4th degree polynomial. It has a very basic U shape. If we ask the questions, how many zeros does this graph has, you would say there's only one 0, and that is down here at the origin, 0, 0. Right? How many turning points does it have? Well, this is a 4th degree polynomial. Our U shape has one turning point down here where it changes from a decreasing graph to an increasing graph. So therefore, we have one turning point, and we have one x-intercept, or 0. So clearing ink. Now we can make this a little bit more dynamic. If I push this over here, it gets a little bit more of that W shape, and we could quickly ask how many x-intercepts, how many zeros? We got 1, 2. How many turning points do you have? Only 1. This is the only turning point in this graph. If you look at this part of it, it curves. It's called the point of inflection that we studied before. It never changes direction, so if it never changes directions, you cannot call it a turning point. So this one still, or this one just has one turning point, just like our other graph did. So try to make it a little bit more dynamic here if I hit the right control. This is the classic 4th degree polynomial, the W shape that a lot of times we'll see. I want to keep a little bit unbalanced here to start articulating a few points. We're supposed to be focused on how many zeros can it have. What is the maximum number of zeros? What is the minimum number of zeros? And how many in between there? Well, I'm going to show you the extremes first. If I move this graph and I do a vertical shift up, I can make it so this graph never touches the x-axis. If it never touches the x-axis, that means we have a minimum of 0. But I could make it so it touches it once, touches it twice. I could make it so it touches it 3 times, and I could make it so it touches 4 times. The illustration here I'm trying to get to is that if it's a 4th degree polynomial, it can have a maximum of 4 zeros and can have a minimum of 0. The other thing we're supposed to focus on is how many turning points can it have. Now the other graphs that we've looked at so far have had only 1, but this graph has 1, 2, 3. 3 turning points. And that's what you're going to see in every one of these evens. If we graph more and more of these and we try to make them more and more dynamic, no matter what I do to this graph, I'm always going to have 3 turning points or 1 turning point, and you can see that. So let's summarize this 4th degree polynomial and move on to more general statements. A 4th degree polynomial known as a quartic. How many zeros can it have? The maximum number of zeros is 4. It could have 3, it could have 2, it could have 1, and it could have 0 because we can slide it above. How many turning points can it have? There's only 2 possibilities for the number of turning points for a 4th degree polynomial. It can either have 1 turning point or it can have 3 turning points. So I think I'll list the others in the other order. So it can have as many as 3, it can have few as 1. And those are your only options. Now, I know we've only studied those 2, the 3rd and the 4th degree polynomial, but from here I want to try to generalize for any polynomial that's either even or odd. So I'll go down here and get a little space. We want to be able to take a look at these powers and when they're even and odd and have a clue of what's going on. So every time we have an even power and every time we have an odd power, we should automatically have some givens, some things that we know for sure. For the evens, how many zeros will they have? It's going to start as high as the power. So let me write this down. It's going to be x to the n. We're saying that this is an even power. So in the example that we had, it was 4. If it was 6, it was 8. Whatever that might be, the maximum number of zeros you can have is the highest that degree is, which is, in this case, n. Then you could have, I'm going to write it down the other way because I think it's a little easier to illustrate. It could have as few as 0, or it could have 1, or it could have 2, or it could have 3, or it could have 4 as we had in the quartic. But what if this is a 6? Then it could go up to 5, 6. What if it's 8? Well, it just keeps accumulating until we get up to the power of n. Bottom line is, if it's an even power, the maximum number of zeros it can have is n, the fewest it can have is 0. Contrast that to the odds. How many zeros can every odd function have? Now this is x to the n, where we're saying n has to be odd. If it is odd, like we had in the third degree polynomial, then the number of zeros that we can have could be as few as 1, but it was guaranteed to have 1. It could have 2. We could have 3. Now that's if it was a third degree polynomial, but we would go up to 5th degree, so then it would be 4 and 5. It's going to go all the way up to the maximum number that we could have is the value of our power. Okay, the clear difference between an even and odd is that evens can have 0 x-intercepts for zeros, and the odds can have as few as, but always has 1. So that's the clear distinction between those two that we got to take notice of. Turning points. We'll try to articulate these through the 4th degree polynomial and the 2nd degree polynomial. If it was a 2nd degree polynomial, it's a U shape. It only had 1, but it has to have 1. If it was a 4th degree polynomial, yeah, it could have 1, but it could also have 3. So it's 1 and 3. So what our generalization is going to be, anytime it's an even power, it can have an odd number of turning points. It could have 1, it could have 3, it could have 5. It's got to be an odd number of turning points, so if it's an even power. So all the way up to, if I want to generalize, if this power is 4, we had to have 3. If this power is 6, it had to have 5. So there's always 1 less turning point than a degree. But the even ones always have an odd number of turning points. You'll see the comparison over here with the odds. If it's an odd power, the turning point, if we are trying to figure out how many turning points the odds have, the smallest odd polynomial that we're going to look at, excuse me, we'll probably just look at our cubic graph. It could have as few as 0 turning points. The cubic could have as many as 2 turning points. So if we try to generalize, and I know we haven't seen a lot of graphs, but you could play around with the 5th degree, but if it's 0, it's 2, the pattern that's emerging is it could have 4 if it's a 5th degree polynomial. If it's a 7th degree polynomial, it could have 6. But the magic rule on this thing is it's always got 1 less than the power. A 3rd degree, the maximum it could have is 2. So whatever this power is, we're going to have 1 less turning point. Now that's similar to what we have over here, but the difference is even functions have an odd number of turning points. Odd functions have an even number of turning points. So that's the distinction between even and odd, and now we're going to go back into our examples here and try to apply that. I just wanted to show it to you in a bigger scale than what they were presenting so far. So our fact function has a rule that says x cubed equal or minus 6x squared minus 27x. They ask us state the possible number of real zeros. So if it's a 3rd degree polynomial, then I've got to be thinking the number of zeros, the maximum it can have is 3. It can go 2, it can go 1, but it can never go 0 because of the opposite end behavior. Turning points. If I want to look at the number of turning points, it's an odd function, so odd functions always have this S shape, so it could have as few as 0, or it could have 2 turning points. And since it's a cubic function, that's all I really have to consider. It's either 0 or 2. Now the next thing we haven't talked about, but it's something that we should be familiar with, and that is determining the zeros by factoring. So really what we're going to be exploring here is how good we are at our factoring techniques. This first example, test your skill if you remember how to factor out a monomial. So the monomial factorization that factors out of all of these is an x. So we can factor out an x, and be left with x squared minus 6x minus 27. But this is still not factored completely because this trinomial can factor again. So don't forget your monomial factor of x. Now we factor into 2 binomials. X squared is x times x. If this sign is negative, excuse me, then we know that these have to be opposite signs. And if they're opposite signs, we're always going to use subtraction. So what numbers can we multiply together to get 27 to get 6 and subtract? And that is 9 and 3. So if this is our factorization, we want to find the zeros of the function. By definition, The zeros of the function are where it crosses the x-axis, and every one of these ordered pairs has an x value, but the y value must be 0. So to find the zeros of the function, we set it equal to 0, and we apply our zero factor theorem to find these solutions. Once it's factored, this strategy is supposed to be easy for finding this. So what is the value of x that we would put in to create an output of 0? And that is 0. If x is 0, we can multiply it by the rest of it, it's still 0. What can I put in for this x? And that's a negative 3. And I can put in for that x, and that would be 9. So there are 3 zeros to this, and we found them algebraically through factoring, which is precisely what they want us to do. Okay, first problem done. Let's try the next one. Our next problem is a quartic. The greatest power on this is x to the 4th quartic. Now, we want to know how many zeros there are. The number of zeros on any even function starts as high as the power, so it starts at 4, counts down, it can have 3, it can have 2, it can have 1, and it can have 0. Just trying to keep in mind, we could slide that smiling face up and it would miss the x-axis entirely, 0. Then turning points. The number of turning points for every even function is always going to be an odd number, and it's always 1 less than the power. So if that's a 4, the greatest number we can have is a 3, and then we can have a 1, but we always have 1 turning point because the behavior of this graph has to have the same end behavior. I don't care if it's a smiling graph or a frowning graph. Since the end behavior is the same, we have to have a turning point in our u or a w. Okay, so we have that part accomplished. Next thing, they want us to take this function f at x equals x to the 4th minus 8x squared plus 15. They want us to factor this to find the zeros of the function. To find the zeros, we're going to force the output to be 0. We're going to use a factorization. Now this is going to stretch some of our factorization techniques. This is a trinomial. There are no monomial factors. There's nothing that we can pull out of an x to the 4th, an x squared, and a 15. So we're going to be forced into factoring into binomials. That's our next stage. The only factors of x to the 4th have to be x squared and x squared. Because this sign is positive, the signs have to be the same, and they both better be negative, so minus and minus. And what are factors of 15 that will give you an 8 if we add them, which is minus 5 and minus 3. Okay, so now I'm going to just make sure that you see that our outside inside, our FOIL, is still intact here. Our first term, x times x, or x squared times x squared is x to the 4th. We take the outermost 2, it's a negative 3x squared. We take the innermost 2, that's a negative 5x squared. And those add up to a negative 8x squared. And then, of course, our last term is plus 15. So I just wanted to illustrate that part of it. It's not that usual or typical for us to have to factor an x to the 4th, but don't give up on those. They will factor. Now what we want to do is figure out from these two factors, what are the inputs that are going to create an output of 0? Well, our factorization process isn't going to work on either one of these because we cannot factor the 5s. But what we can do is we know that x squared minus 5 has to equal 0, or x squared minus 3 has to equal 0 in order for our zero factor theorem to apply. One of these two numbers has to equal 0 in order to get an answer from 0. So we can solve each of these two equations separately, and then we would be able to say that we know that x squared would have to equal a positive 5. And that means if we want to find x, we have to undo squaring, which is square root. When you square root, don't forget you have both the principal and the minor root, so it's plus or minus square root of 5. Because of the squaring, we have both answers that come along with this, because we square a negative, it's positive, and we square a positive, it's positive, and we have two solutions coming from that one. We also have two solutions coming from this one because we know that we'll have x squared equals a 3, so x is equal to plus or minus the square root of 3. So now we found all 4 zeros of this function by factoring. And the ordered pairs are going to be plus or minus square root of 5, comma, 0. The other set would be plus or minus the square root of 3, comma, 0. So factoring is going to be important. We're going to have to make sure that we are carefully factoring and going through our factorization process correctly, but that's the anticipation and the expectation that we have to find zeros algebraically.